So those were the reactions that come under nucleophilic addition, like some of them, examples, like the ones whose products have like some sort of a significance. That's what we've seen a bit. But all the nucleophilic addition, like if you see that there's a nucleophile, carboxylic acid, sorry, aldehydes or ketones means they undergo addition reaction. Double bond becomes single bond. Okay. The next set of reactions we'll be looking at. So if nucleophilic was the first one, this would be the second set of reactions, reduction reactions. So what do you get when you reduce aldehydes ketones? So on reducing aldehydes, you get this is something that you have.
Alcohol.
What sort of alcohol?
Primary.
Yeah. Primary alcohols with aldehydes. And ketones say what sort of alcohols? Secondary alcohols. Okay, so the only like I don't know new thing that we'll be looking at would be the different reducing agents. LiLH4 is a pretty strong reducing agent. You directly get, you can get alcohols, can get alkanes. No, yeah, alcohol hai na? So you won't have any more unsaturated things. So you'll get alcohols only. So yeah, the first set of reducing agents you can use would be with NaBH4 or LiLH4. These are hydrides, and they just add the hydrogen across the double bond. That's it. So you have C double bond O. Using these reagents, NaBH4 sodium borohydride or LiLH4, hydrogen added, so this becomes CHOH. That's it. The second one, this is a named reaction. So yeah, just note down this, like this you already know, so you can note it down in short form. It's pretty easy. The other one, this is called Clemenson's reduction. Reduction. So the reagent that you use in this case, since it's a named reaction, put in red, C double bond O. Use
This B, sorry, the B before reduction, so like A was nucleophilic addition, Vesa.
Yeah. Actually, the second part, this will treat it as two different reactions. Okay. So with the hydrides, it's a very straightforward reduction where hydrogen is added across the double bond, and that's how you get alcohols. There's a few, like couple of other reducing agents we'll be looking at. One is Clemenson's reduction. This is going to reduce it directly to alkanes. So we're going to get rid of the oxygen also. So how it happens is, first step, use zinc amalgam in hydrochloric acid. So this is Clemenson's reduction. So you just get CH2 plus H2O. So you're taking it one step further where the alcohol itself is reduced to alkanes. And then you have another reaction. So let me know once you've finished noting till here, then look at the other one. Right. Kaveri, Sanskriti, guys, let me know when you finished.
I'm done.
Okay.
Done, ma'am.
Smera, you finished noting, right? Okay. Arya and Sia.
Yeah.
Okay. Sia still.
Done, ma'am.
Okay. The next one. So this is called Wolff-Kishner reduction. So that's WLFF-KISHNER reduction. This also reduces it direct to all the way up to alkanes. This is a two-step process. The first step, you literally just studied it. So you start off with your aldehyde or ketone, treat it with hydrazine, that's NH2, NH2. So
Ma'am,
yeah,
when is the break? Can we have a break?
oh, after this, so we'll finish off. This is the last reaction in reduction. So we'll take 5 minutes and then go to oxidation.
Okay.
Yeah. So what product do you get in this? You literally just noted this down. So,
Imine.
huh?
You'll get a no.
Hydrazine, NH2, NH2.
Oh, sorry.
Hydrazone.
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 And one H goes and then H2O goes. So this becomes NH2. So hydrazone. Now this hydrazone, you are going to heat it with KOH, alcoholic KOH, except you're going to use ethylene glycol. So this is going to cause like, okay, this is going to reduce it to alkane. So this O just gets substituted with hydrogens and there's nitrogen being released. Okay, so for usually when we take alcoholic KOH solutions, we use ethyl alcohol and KOH, right? But the reason why we want specifically ethylene glycol is because this is a high boiling solvent. And we are going to do this reaction at a high temperature because hydrazones, they tend to be slightly unstable. They're pretty volatile. They can catch fire easily. So so basically for this reaction to take place, we want to do it at a higher temperature. CH2OH, uska boiling point is very low. So we want a higher boiling solvent, which is why we use ethylene glycol. Not to do with hydrazone, but yeah, in order for this reaction to take place. Okay, so this is, yeah. So note this down and then it's 519, right? So take 5, let's meet back at 525. Uske baad, we're going to look at oxidation reactions.
That's the last set of chemical reactions, right?
No, there's a total 5 types of chemical reactions. We have nucleophilic addition, reduction, oxidation, and then we have aldol condensations, like reactions involving the alpha hydrogen. Aldol condensation cross aldol is another major thing. And then there's like other reaction, like chote, smaller ones, 2, 3 of them.
Is break now or after oxidation?
Let me see oxidation mein kitna. No, we'll take it now itself because oxidation may we have quite a few reactions. It get heavy.
Okay.
Until 5:30.
5:30, yeah. Then class will be till 6:30. Is that okay?
6:50.
Isn't it?
Isn't it always till 6:30?
Guys, miss, you just pretend like you give us till 6, but you actually take till 6.
Yeah, that's because like there's lots of breaks and things involved. And then I usually spend the last doubt like a few minutes just clarifying doubts and things like that. So that just gets cracked on.
Yeah, it's fine till 6.
Okay.
We'll take break till 5:30.
Okay. Cool. Like get something to eat or something. Okay. Yes. Oxidation, the first bit of oxidation is pretty straightforward. Um, let's take it one thing at a time. So first, aldehydes. Because aldehydes are at the corner of the chain, if you oxidize them by adding an extra atom of oxygen, what do you get?
Carboxylic acid.
Carboxylic acid.
Carboxylic acids, absolutely right. Here, let's call it carboxylic acid. So oxidizing agents that you can use in this process, a couple of them you guys know very well. Which are the oxidizing agents that you can use?
K2Cr2,
Completed.
KMNO4, K2Cr2O7.
7, yes. Dichromate. We have KMNO4. There's another oxidizing agent that you can also use, nitric acid, HNO3. Okay. But when it comes to ketones, if you're trying to oxidize ketones,
We'll require a strong oxidizing agent like KMNO4 to
yes,
convert it into an acid.
correct. We need strong agents, and we also need a higher temperature than normal, like compared to aldehydes. And what acids are you going to get from ketones? Is it like a direct conversion, or what happens? So in ketones, we'll see that the carbon chain is broken wherever the C double bond O is there. So we have CC bond cleaved acids. So for example, if we start off with the acetone, so if we start with CH3, C double bond O, CH3, we end up getting a mixture of like there is going to be the carbon chain is going to break, and we end up getting a mixture of formic acid, HCOOH, and acetic acid. Okay, so it can break over here, it can break over here. So that is not something that we can control, but what we end up getting is carbon chain being broken and a mixture of acids. So we get CC bond cleaved acids. Okay, so this is the simplest ketone. This is pretty symmetrical, so it's easy to predict. Yeah, so once you guys have noted till here, we'll take another example of a bigger ketone. Right. Sia's not here yet.
She is. No, I'm here. I finished.
Okay. Noted. ठीक है. Everybody finished noting. ठीक है. Let's take a bigger like unsymmetrical ketone. So for example, if we have pentane 2-one. So if this was treated with a strong oxidizing agent, let's say KMNO4 in sulfuric acid, what products can you get from this? So it's going to be a mixture of products. So either this bond can break or this bond can break. So suppose this bond breaks. So I'll just color code it. So suppose I have the bond between C1 and C2 breaking. Then this will be an acid. So I get formic acid, HCOOH, plus this whole thing will be another acid. So I get CH3, then CH2 taken twice, and then COH. So butanoic acid. You may also see that like there's also a possibility of this bond breaking. The bond between C2 and C3. In that case, I'm going to get so these two. So that's CH3, COOH, acetic acid, plus next 3 carbon atom acid. So that's propanoic acid. CH3, CH2, COH. So there is like isme se there will be one major product and one minor product. So usually what happens is, um, in this sort of a situation, whenever you have an unsymmetrical ketone, the C double bond O preferentially stays with um, the smaller, like on the side of the smaller alkyl. So acetic acid is going to be like a major product comparatively. So basically, the C double bond O, this particular group, preferentially stays with the smaller alkyl group. So it's still going to be a mixture of these acids, but out of that, so this is going to be like slightly on the higher side. It's going to be the major product.
So we will have all 4 as products.
Yeah. So you're going to get a mixture of all of these. Okay. Next.
Preferentially, what with
Stays.
stays?
Like double bond. So obviously there's both the possibilities are there, right? So either there can be a bond break over here or a bond break over here. So the preference is usually leaning towards C double bond O, staying with CH3. So this side of the chain gets oxidized because of the strong oxidizing agent. C double bond O is retained with CH3. So that's what it leans towards. But again, this is like a violent reaction. It's a fast reaction. So it's difficult to predict or control where the bond is going to break. So the next set of reactions are all oxidation reactions only, but they are also used as tests for aldehydes, like mainly aldehydes versus ketones. Yeah, so different tests for aldehydes and ketones. Okay. So out of these, uh, the first one we'll talk about is tolerance test. So these tests are kind of important. Like you have lab practicals also based on these reactions. But because they're named reactions and they're like tests for different aldehydes and ketones, they kind of, a lot of questions will be asked. So these also will be taken as a hint. Like, suppose you have a mystery compound, like a organic compound with the formula C something, H something O. It undergoes reaction A, it undergoes reaction B. And then if they say, okay, this also shows tolerance test or gives a silver mirror with tolerance reagent, that's a hint for you that, okay, so this could be an aldehyde. This is not a ketone. Okay. So tolerance test is done with a tolerance reagent. Tolerance reagent is chemically it is ammoniacal silver nitrate solution, and this is prepared uh, during, like, at the time of the reaction. This is not something that you can prepare in advance and store it in bottles. You need to prepare just before the reaction. So from the name, it's basically a mixture of ammonia and silver nitrate in water. So when you prepare this, chemically you end up getting this. So you have RCHO plus a complex of ammonia and silver ions, this cation, plus OH minus in the from the solution from water. So this is to balance it. So the aldehyde gets oxidized into carboxylic acid group, RCO minus, and the silver itself is reduced into elemental silver. So you get 2Ag plus H2O plus NH3. Okay, this is Tollett's reagent. This is Tollett's test ka reaction. And this oxidation will undergo only for aldehydes. Ketones will not undergo this reaction. So this is a test for aldehydes. If it is an aldehyde, silver is produced. So this, to our eye, you can see it as a silver mirror in the test tube. So that is why this is also called silver mirror test. Okay, so I'll show you guys a visual. So on the test tube, originally what you take is a transparent solution, but if it's an aldehyde, the test tube is lined with silver. So it kind of looks like a mirror being found there.